All right, guys, I hope this works now. I am discussing the transformations. Now, the transformations, guys, allow you to move different functions all over the XY plane. So what I want to do is focus on a few functions in particular that I would like to go ahead and transform. So starting off with the quadratic function. Now, for the quadratic function, guys, you have to be able to, given a quadratic function, also referred to as an x squared function, okay? If I give you the equation, you have to have a mental picture of what the graph is going to look like. Now, keep in mind, the domain of quadratic function is all real, so it would go from negative infinity to positive infinity, while the range is restricted to all y values, all values greater than or equal to or 0. Now, when you graph a quadratic function, by the way, the f of x equals to x squared function in regards to the quadratic function, guys, is referred to as the parent function. And as the parent function, we have the vertex, which is also known as the turning point, at the origin, right here, guys, the origin at 0, 0. So your basic quadratic function f of x equals to x squared has its origin at 0, 0. Now, by affecting the inside and the outside of the function, that moves the function all over the xy plane, guys. So that's the first function we're going to focus on. The next one we're going to look at is the absolute value function. Now, for the absolute value function, by the way, guys, I forgot to mention that the quadratic function looks like a letter U when it's opening up, okay? And so the absolute value function resembles a V-shaped graph, a V-shape for absolute value, guys. The equation of an absolute value, the parent function, is the absolute value of x. Now, just like with the quadratic function, guys, the domain is not restricted at all. The domain is all reals from negative infinity up to positive infinity, while the range, just like with the quadratic, is restricted to all values greater than or equal to 0. And remember, guys, it resembles a V-shaped graph, like the quadratic resembles a U-shaped graph. So we're going to go ahead and go to the XY plane once again. When we're graphing the absolute value function, remember, the vertex is located at 0, 0, just like with the quadratic function. But guys, when you graph an absolute value, it's going to be shaped like the letter V, look like the letter V. So it's a very sharp graph. So there aren't any curves to it. It's very sharp because this actually represents the graphs of two linear equations pretty much, okay? So that's the second function we're going to use to do the transformations. Now, the last one we're going to use to do the transformations is the square root function. Now, this might be a new one that you haven't seen before. When we talk about the square root function, the equation is f of x equals to the square root of x. Now, think about a square root, guys. What values can you take the square root of? You can take the square root of a positive value. You can take the square root of 0. But you cannot take the square root of a negative because that's going to lead to an imaginary value. So this means that the domain is restricted to all values greater than or equal to 0. And then the range is restricted to all values as well from 0 up to positive infinity. Now, if you want something to help you remember what the graph is going to look like, the graph of a square root function, you could say it looks like a check sign, something like that. Or you could say it looks like the swoosh on the Nike shoes. Or most people, they actually see a square root, okay? So it really doesn't matter, guys. Whatever works for you, so you just go ahead and use that. So let me go ahead and go to the XY plane. You know what? Let me redraw this one because I want to focus on a particular area. Because remember, guys, we're talking about the square root function. The domain is restricted to all x's greater than or equal to 0. The range is restricted to all y values greater than or equal to 0. So that means that the square root function is exclusively in the first quadrant, okay? So when you graph this, guys, positive x values, positive y values as well. So you input positive x's, what do you get out? positive y values. So these are the three functions we're going to look at. Now, guys, I am not going to be looking at all the transformations with you. I'm only looking at 4 of them, starting with the vertical shifting. Now, the vertical shifting, it occurs outside the function, and it moves the function f of x up or down in the same direction. So if you've got f of x plus c, this plus c on the outside moves the graph up c units. Now, if it was f of x, my pen is not writing again, f of x, okay, Shazam, okay, we're gonna get that, minus c, that minus c would move the graph down c units, okay? So the vertical shifting occurs outside the function and it moves the graph up or down in the same direction. So let's look at some quick examples, guys. Let's say we were going to shift the absolute value function. The original absolute value function looks something like this. But let's say I were to go ahead and do absolute value of x plus 3. So what would that do to the original function, guys? Here's what it's going to do to the original function. So that plus 3 there, rather than starting the vertex at 0, it's going to shift the vertex up 1, 2, 3, and then every single point on the graph, by the way, is getting shifted. The y value of every point on that graph is getting shifted up by 3 units, guys. So this is where the new graph would be located at, and the vertex would be at 0, 3. So for example, if you had a point on the original graph at 2, 2, and then you were to go ahead and shift that function up 3 units, so this new point would actually be over here somewhere at 2, 5. Remember, every y value is getting shifted up 3 units. All right, so let's do it again. This time, guys, we're going to do f of x is equal to the absolute value of x minus 2. Now, for the absolute value of x minus 2, what you have to realize is this, guys, that minus 2 on the outside is going to move the function down 2 units. So we go to the xy plane, find where y is equal to -2. Every single point on the graph is going to get shifted down 2 units. So the resulting graph will look something like this, guys. So we're still retaining the same shape. The only thing that is moving is actually the vertex. So the vertex is no longer at 0, 0, but rather it's at 0, -2. All right. So again, if we're talking about this coordinate point 2, 2, and we're to go ahead and move the function, shift the function down 2 units, that point 2, 2 will actually go down to 2, -1. I know. All right. So guys, that is what's happening with the vertical shifting. Now I'm going to move on to the next transformation. And the next transformation has to do with the horizontal shifting or translations. Okay. Horizontal translating or shifting, same thing. Shifting or translating. When we talk about the horizontal shifting or translating, it moves f of x left or right, and this is key here, guys, the opposite direction. By the way, this one is occurring inside the function, guys, inside f of x. So it's going to move the function in the opposite direction. So what in the world am I talking about? Well, let's look. If you have f of x plus, let's say, a c value over here, okay, the c value, it's a plus c, it would move the graph left in the opposite direction, c units. So it moved the graph to the left, c units. Likewise, if you had f of x minus c, okay, f of x minus c, now that minus c right here would move the graph in the opposite direction, so it would actually move the graph to the right, c units. Okay, so what in the world am I talking about? Let's do some concrete examples. Let's say I have the quadratic function, f of x equals to x squared. When I graph this, you know, the graph is located at, the vertex is located at the origin, so the graph looks something like that. Now, if I wanted to horizontally shift this graph, I could rewrite this as f of x equals to x minus 3. That minus 3 right here, guys, is going to take the vertex from 0, 0 and move it right 1, 2, 3 units. So now the vertex has been shifted to the right 3 units, and then we're going to do a rough sketch of the graph. This is just a rough sketch. This is not a precise graph, guys. So every single point on that graph is being shifted to the right, okay, 3 units. So guys, this point will now be at 3, 0. Remember, it's on the x-axis. Whenever you have a point on the x-axis, we're looking at the x-intercept. The y value is always 0, and then the x value will be some number. So what if instead we did f of x is equal to x plus 1 squared. Now that plus 1, guys, is going to take the graph from the origin and move it over to the left, opposite direction, to the left, 1 unit. So the new vertex is going to end up right here, okay? So now you're going to do a rough sketch of the graph, guys. This is just a rough sketch. This is not a precise graph. So this is what it's going to look like. So now your new vertex is going to be at -1, 0. By the way, I keep talking about the vertex. The vertex is the turning point of the graph. So the vertex is located on the absolute value as well as on the parabolas. Now, on the square root, I wouldn't necessarily call it a vertex. I would call it a starting point or an initial point. All right, guys. So that's second transformation. Now, here comes the third transformation I'm going to talk about. Now, the other ones, I'm going to briefly mention them, but I'm not going to focus on them that much because we're going to save those for the upper level math courses, especially since, you know, we're only surface teaching this. So guys, here's the next part, and that is the reflections over the x-axis. We're going to look at first. By the way, guys, when we do the reflection over the x-axis, that's the first one, it occurs outside f of x and opens the graph of f of x downwards. So in other words, it opens the graph towards the negative side of the y-axis. So guys, once again, that negative on the outside allows the graph to reflect across the x-axis, and when it's reflecting across the x-axis, basically it shifts the opening of the graph from opening towards the positive side of the y-axis, but rather it opens down towards the negative side of the y-axis. So guys, let's see what I'm talking about. If we're talking about, let's say, the absolute value function, if you go ahead and graph the regular absolute value function on the xy plane, it looks like this. But if you're going to do a negative, okay, let me use a different color, a negative absolute value of x, every single y value on that function will be affected. So you would no longer have a graph opening up towards the positive side of the y-axis, but instead it's going to open down towards the negative side of the y-axis because every single y value, guys, will become a negative, okay? So basically the x-axis reflection opens the graph downwards towards the negative side of the y-axis. So guys, here comes the next one. If we're looking at, let's say, a quadratic, f of x is equal to x squared, okay? So typically the graph of a quadratic looks like this. But if we are going to transform this so that it reflects over the x-axis, this would have a negative leading coefficient, and that negative leading coefficient will allow the graph to open downwards towards the negative side of the y-axis. In other words, it's decreasing on the left to negative infinity, and it's decreasing on the right towards negative infinity. So the graph is decreasing. This one is increasing. The parent function is increasing, but the reflection of the graph is decreasing. All right, guys. And then here comes the third one. And the third one we're looking at is the square root function. Now, for the square root function, guys, I'm also going to mention reflection about the y-axis. When you graph the square root function, the graph is exclusively in the first quadrant. Now, if you want to reflect it over the x-axis, every single y value will become a negative. So when we reflect it, the graph is going to look like this. Yeah, okay? Now, out of the three functions that we're talking about for the transformations, the only one that can be reflected about the y-axis, guys, is this one right here, the square root function. So when we're reflect over the y-axis, this one is going to occur inside f of x, inside f of x. So rather than f of x increasing towards positive infinity, okay, or the graph instead is going to face in the opposite direction, okay? And so it would be decreasing, okay? So guys, let's go ahead and look and see what I'm talking about. And remember, this is happening inside the function. So the graph, oh, I forgot to mention the function for this, guys. Oh, I'm leaving stuff out. I think I need to slow down a little bit sometimes when I'm rushing like that, guys, because I don't want to make the video too long. So I'm trying to get through all the information without, you know, missing anything, but sometimes I do, okay? So guys, that f of x equals to the negative square root of x, you notice the negative on the outside, that is what's causing the graph to reflect over the x-axis because every y value will become a negative. But if you want to reflect the graph about the y-axis, it has to happen inside the function. So there's the negative inside the function. So what is that going to do to the graph, guys? Rather than the graph opening towards the right, the graph is now going to open towards the left. Now, I know what some of you are saying. Wait a minute. I thought we couldn't have any negative values under the root. You're absolutely right. But guys, what if we were able to find x values that could cancel out the negative inside the root? For example, if we were to substitute a -1, a negative and a negative becomes a positive. When you take the square root of +1, you get 1. Likewise, if we were to go ahead and plug in a -4 into this function right here, okay, a -4 becomes +4, and when you take the square root of it, what do you get? +2. So guys, if we were to go to the XY plane and graph these points on the XY plane, 1, 1 would be located right there. And then 4, 2 would be located right here. -4, 2 would be located right there. So it works. And out of the three functions we're looking at for the transformations, the only one that reflects about or over the y-axis is just the square root function. The other ones will not. And the reason why is because they're even functions, but we really didn't even talk about that in this class. So don't worry about that part, guys, okay? All right, guys. So anyways, let me go ahead and do a few examples with this. And then I'll mention a couple more of the transformations I did not talk about because I'm saving those for the higher level courses, okay? So guys, I am going to put all three transformations together. So we did vertical shifting, horizontal translation, horizontal shifting, and then reflections. Okay, so I'm going to do 3 examples, and I'm going to use all 3, guys. Okay, so this one is the absolute value, negative absolute value of x plus 2, and then minus 3. Now, remember the parent function, guys. Always start at the origin. Start at the origin. Start at the origin. Notice I repeated that a couple of times. I'm making a point, okay? So guys, for this problem, first, you got a negative leading coefficient. That means that the graph is going to open down. This -3 on the outside is saying the graph is moving down 3 units. And then, of course, the 2 inside is moving the graph to the left 2 units, okay? So guys, we're going to do this one step at a time, starting at the origin. So we're going to start at the origin. We're going to move to the left 1, 2 units, and we're going to move down 1, 2, 3 units, plot the coordinate of the vertex, and then sketch the graph and make sure it opens downwards. Now, guys, listen. These are not precise graphs, okay? We're just rough sketching. But let me go ahead and mention something here because we talked about this already, the y-intercept. It's easy to find the y-intercept. By the way, the y-intercept is in this chapter that we're currently talking about on functions. So one of the points we can actually figure out is the y-intercept. So if we were to go ahead and plug in 0 in for x, that's how we find our y-intercept. We plug in 0 for x and solve for y. So look at what we end up with. 0 plus 2 is 2. Absolute value is 2. Okay, so we get negative 2 minus 3, which gives us a negative 5. So the y-intercept would end up somewhere over here, guys. And that's close enough, guys. That is close enough. Come on now. That's really, really close. And then, guys, remember how I said these functions are even? What I mean by that is that they reflect across a line called the line of symmetry. That's for later on when we're graphing the quadratics, but for now we're just doing rough sketching. So you could actually reflect this point across the line. That's for later on, guys. We'll save that for later, okay? So that was the first example. Here comes another one, guys. This time I'm going to do a quadratic, okay? So for this one right here, I am going to do f of x is equal to a negative x minus 2 squared and then plus 3. Okay, so again, let's brainstorm. Let's analyze this, guys. The leading coefficient is negative, so which means the graph is going to open down. We got a minus 2 inside the function. That means that the graph is moving to the right 2 units, right 2. And then this positive 3 on the outside is saying the graph is being shifted up 3 units. So it's being shifted up 3 units, shifted to the right 2 units, and it's going to open down, guys. So again, when you are sketching the graph, guys, always start where? At the origin. Start at the origin. By the way, I haven't been mentioning the graphing calculators, but yes, you can do this on a graphing calculator too, guys, okay? So let me go ahead and rough sketch this for you. Okay, so let's go ahead and look. Now on this one right here, guys, I am going to start at the origin. I'm going to move right 1, 2, okay? And then I'm going to move up 1, 2, 3. And I'm going to plot the coordinate of the vertex right there. Now remember, the shape of this graph is a U-shaped graph, but it was opening down. It is a quadratic graph, so when we graph it, guys, it's going to look something like this. And that's it. Now, why not? Let's go ahead and find the y-intercept, guys. Since we did it for the last one, we might as well do it for this one too. To find the y-intercept, we're going to go ahead and plug in 0 and find the value of f of 0. So negative 0 plus, minus 2. And then we're going to square it and then add 3. Negative 2 squared is 4. So we get negative 4 plus 3, which gives us a negative 1. Okay, so that means that the y-intercept, I missed it. It was kind of like way down here, guys. So this one needed to be a skinnier graph, okay? So I missed it, okay? But remember, we're just doing rough sketchings. We're not doing precise graphs, okay? And then one more, guys, and that is with the square root. Now for the square root, we're just going to do a negative leading coefficient, x minus 2, and then plus 1. So on this one right here, guys, let's analyze the graph. There's a negative, so the graph is going to open down towards the negative side of the y-axis. The minus 2 inside the function is going to move the graph right 2 units, and then the plus 1 is going to move it up 1 unit. Always start at the origin, guys, start at the origin. So you're going to go ahead and start at the origin, go right 2, so that's 1, 2, and move up 1. So it's going to take you right here. Remember, which way is it opening? It's opening down towards the negative side of the y-axis. Bam. And that's it. Yeah, guys. Okay, so let me just say this. There's also a vertical stretching. And by the way, when the graph is stretching, it looks very thin. It gets closer to the y-axis. And then there's a vertical shrinking. When the graph is shrinking, it looks like a wide graph. It's getting closer and closer to the x-axis. When this happens, guys, it happens outside of the function with the leading coefficient. If the a value is greater than 1, I'm going to put absolute value. It is being stretched vertically. Think of a rubber band. Okay, now if a is less than 1 but greater than 0, then it is being it is going to shrink vertically, okay? And guys, be careful with this one. So vertical stretching happens on the outside. I'm not going to emphasize this. We're not going to talk about it ever again. So that's it. And then last but not least, there is a horizontal stretching and shrinking too. Now, this one happens inside the function, inside. It's happening inside f of x. And so for this one right here, guys, you will see something like this. F of x is equal to maybe 2 x to the second or something like that. That's not a really good example. Let me go back a little bit. All right, so let's do this. 2x minus 3 squared, okay? So this 2 here is going to affect what's going to happen with the horizontal part of the graph. Now, we don't stress this as much. The one that we stress the most is the vertical stretching and shrinking. So when you guys are doing the these particular transformations, you're not going to have vertical stretching or vertical shrinking. You're not going to have horizontal stretching and shrinking, but just so you know, okay, this is going to happen inside the function, okay? So if you're looking at inside the function, you're looking at something like this, perhaps, okay? Let me see here, a and then times x raised to the x squared. So this a value here is going to determine whether or not the graph is going to stretch or shrink, guys, okay? So that's all I wanted to mention to you guys about the transformations. Obviously, when we get to class, we're going to go ahead and talk some more about the vertical stretching and shrink, not vertical stretching and shrinking, the transformations, guys. 3 transformation. Vertical transformation, where you go up and down. Horizontal transformation, where you go left and right. And then the reflection. Just those 3 I want to focus on. Keep it very basic, guys, okay? So until next time, bye, everybody.